So our second invited speaker is Emina Torlaak. Emina received her PhD in 2009 from MIT, and there she was well known for working on COD, a constraint solver for a relational logic that was found in the Alloy model checker. And since then, she has worked at a number of places, including, as far as I can recall, IBM Research, Logic Blocks, and UC Berkeley. And she's now an associate professor at the University of Washington. And in the last 5 years in particular, she has been well known for developing Rosette. That's a system which puts a symbolic execution engine in the hands of programmers and allows them to develop so-called solver-aided tools, ideally almost as easily as they would write an interpreter. So I think this is a quite fascinating line of work, which I'm looking forward to hearing about in this talk. So please welcome, join me in welcoming Emina.
That should do it.
Thank you.
Well, thank you, Francois, for the introduction, and thank you all for being here. It is my pleasure to attend my first ICFP and tell you all about solver-aided programming. So briefly, solver-aided programming is a new programming model that integrates automated theorem provers, specifically SMT solvers, into a programming language. It does that at a very high level so that you can actually, within your programming language, call the solver without having to call the solver. You don't have to generate any constraints in order to perform program verification and program synthesis. When you embed a solver into your language in this way, what happens is you enable a very wide range of people from, of course, first-year grad students, always our target audience, to professional software developers, to undergrads, and to even high school students to build state-of-the-art synthesis and verification tools based on SMT solving for various domains for which such solvers or such tools couldn't otherwise exist. Because without a programming language or a solver-aided programming language, building one of these tools is extremely hard, especially state-of-the-art one. It takes person-years of work and expertise in programming languages, formal methods, and so on. So this talk today is going to focus on Rosette, which is the solver-aided programming language that I've been working on since 2012, a long time. But it's still a fun topic, and I'm still excited about it, and I'm hoping to convey some of that excitement to you today. The talk will have 3 parts. First, I'm going to define what I mean by a solver-aided tool. So I'm just going to show you what those tools actually look like, why you might want to have one for your domain, and why it's usually very difficult to build one, why it takes such a long time, and why does it take so much expertise. Then I'm going to introduce this notion of solver-aided languages, specifically Rosette, and we're going to see how Rosette lifts this burden, how it makes it possible for somebody who doesn't have any expertise in formal methods, for example, to build a verification tool by essentially just writing an interpreter. And I will also give you a flavor of how Rosette works. How did it actually accomplish this under the hood? Finally, I will talk about some of the applications of Rosette. Since its first public release in 2014, it has been used to build over 30 tools, synthesis and verification for various domains, and by a very wide range of programmers, and they have been applied to a wide range of code bases. So anything from open source code, such as critical components of the Linux kernel, to safety critical software that controls a radiation therapy machine at the University of Washington. So I'm going to be talking about some of those applications at the end. Of course, there are 30 of them, so if you want to hear more about some of them that I'm not going to talk about, please talk to me afterwards, and I'll be happy to chat. All right, so let's start by talking about SolverAided Tools, what they are, why you might want one, and why it's hard to build one. At a high level, programming is essentially a task of translating a specification that you have in your mind to some code that a computer can execute. Normally, when you're programming in a programming language that you're familiar with that doesn't have any kind of solving support, the way that you check that your program satisfies the specification is essentially by testing it on a few inputs. So what I've done here is I have encoded what it means for my toy program or my example program P to be safe in some function in the same language. And I'm testing that the P is safe on the input too. So the function takes the X, which is the input on which you want to run P, and the output of P, and checks that it satisfies some safety predicate. So there's a specification. This is what we do in a normal programming language. We write assertions, we test our code. Now, when you bring a solver into this loop, something interesting happens. Now you can ask the solver about the behavior of your program on all possible inputs, not just one. The way that you do that is by reformulating your question about the safety of P, in this case, as a question about some arbitrary integers. So in this programming world, we can now write X to stand for an arbitrary integer. We can assert that hopefully P is safe on X, and what the solver is going to do is actually check that this assertion holds on all integers. So once you have this ability to express symbolic values and this ability to express assertions, you can ask interesting queries. The one that I just described is the classic query that we build on top of SMT Solver, and it is verification. The way that the tool discharges this query is by encoding the semantics of your program in an underlying logic or a combination of logics understood by the SMT Solver, and then asking it to search for a model of this formula. So the formula is saying that there exists an X such that P is not safe on the input X. So it makes this predicate false. And here I'm using the bold font to denote the semantics. So the meaning of P encoded as a formula, and same for the meaning of safe encoded as a formula. Okay? So if there is model or a solution to this formula, it is a concrete counterexample to the correctness of P, right? It is concrete input X on which the P violates the specification, and in that case, let's say that X is 42. Okay, now that we have found an input on which our program fails, the next thing we might want to do is actually debug it. And the solver can help with that as well. So what the tool is going to do now is issue a query to the solver that looks like this. So the query says that X is equal to 42 and P is safe on X. So what can you tell me about this particular formula, given that you know that X is actually, that the program is unsafe on 42? What can you tell me about this formula? It's unsat, right? So even though the formula is unsatisfiable, the SMT solver can still help you. It can return something called a minimal unsatisfiable core, and when you lift that back to the constructs meaningful at the level of the programming language, what you get is a minimal subset of expressions in the program such that you have to modify at least one of them to make the program pass the assertion on the input 42. So let's say that this expression X plus 2 here is faulty somehow. And in order to fix it, we have two choices. So one expensive choice is a runtime repair, where we actually replace this expression with a call to some magic function choice. Think of it as Floyd's choose operator, non-deterministic angelic choice. And at runtime, the solver will be invoked, and it will return a correct value such that the rest of the program will execute without any assertion failures. Now, if you don't want to run your solver at runtime, you have another option, which is to replace that buggy expression with these double question marks. They indicate to the program synthesizer to search a space of expressions in the same programming language as P, such that when you substitute the expression E that you found into that hole, then the resulting program is safe for all inputs X. So this is the program synthesis query. So this is the range of things that you can do if you bring a solver into your programming language. Now, the thing that you will notice so I presented a range of different tools. These are by no means the only tools. You can build many other tools on top of a solver, but they all kind of look like this. What all of these queries have in common is that you essentially need to have a way to compile the semantics of your program to constraints, right? You have to be able to express the semantics as some formula in first-order logic that the SMT solver can understand. And building this encoder, this translator, this compiler is essentially what takes a really long time normally. For any kind of a non-trivial programming language, this is a very hard task, takes many person-years of work, lots of expertise, and so on. What Rosette helps you to do is essentially avoid building this compiler. So instead of building a compiler from your programming language down to constraints, what you do instead is you simply write an interpreter for your programming language. And that's all you do. The catch is you write your interpreter in a language that itself has a symbolic compiler. So the one in Rosette is called a symbolic virtual machine. When you execute your program on top of your interpreter on top of Rosette, it will generate those constraints for you and send them to the SMT solver and communicate with the SMT solver on your behalf. The hard technical challenge that Rosette addresses is actually how to do this reduction efficiently. Because I just told you it's really difficult to build a compiler for a single programming language, right? It takes programming that language and translates to constraints. Rosette is promising to solve an even harder problem, right? It is trying to translate a composition of your program and an interpreter for your programming language down to constraints for you. And we're going to see somewhere in the middle of the talk how Rosette actually does this. All right, but the first thing that I'm going to do is I'm going to show you how to use Rosette to build a verifier, a debugger, and a synthesizer for a very simple programming language. And then we're going to see how everything works. At a high level, building a tool in Rosette is essentially a task of embedding a domain-specific programming language into a host language. Okay, so here I'm using the phrase domain-specific programming language in a very generous way. It's a formal language that's specialized to some domain. It can be Turing complete. It doesn't have to be. It doesn't actually matter. And I build it by writing an interpreter or a library. So to show either deep or shallow embedding in some kind of a host language. And the host language is usually something that has metaprogramming features, so something like Racket or Scala or JavaScript and so on. And here are many examples of domain-specific languages, some of which I think most of you have used at some point. So now you might be wondering why this focus on DSLs. And it turns out that DSLs are useful, right? People build them all the time. And there are two primary reasons for that. And they're best illustrated by an example. So here is an implementation of matrix multiplication in a linear algebra DSL, so something like Eigen or MATLAB. And here's the same implementation in C++ and Java. By looking at these two implementations, you can see two things. All right? The first thing, the obvious thing, is that the first one is much shorter. So the DSL provides the right construct to express and solve problems in that domain. And of course, the less code you write, the fewer opportunities are to introduce bugs. The other thing that's interesting is that a domain-specific programming language, the compiler for that language can exploit domain knowledge to generate better code. Or if we're talking about a programming tool, it can exploit that domain knowledge to generate better constraints and enable more efficient solving. So those are the reasons why we're generally focusing on domain-specific tools via domain-specific languages. If you look at successful SMT-based projects for verification, synthesis, and so on, all of them are heavily specialized to the domain. And that's precisely because we have to make heavy use of domain knowledge to exploit it to generate constraints that are solvable in reasonable time. Okay, so you build tools in Rosette by building a language, and you do it in exactly this way. So you build either an interpreter or a library in a SolverAided host language, in this case Rosette. And Here are some things that have been built with Rosette. I will be talking about a couple of these in details, but I'm just listing some to give you an idea of what kind of domains we can handle in this way. So basically anything from very high level domains such as education and games down to very low level domains such as verifying system software, specifically security monitors, which is something that we're going to talk about later. Okay. So this is the high-level picture, how you would build a tool in Rosette. So let me tell you now what Rosette actually is. What does it look like? It is an extension of Racket. Specifically, it adds to Racket 3 kinds of constructs. So if you remember when I was describing to you how SolverAided tools are built, there were 3 ideas that I emphasized. The first one is the ability to introduce symbolic values into your programming language, right? To tell the programming environment, here's a value of type integer, and that's the only thing I know about it. It's an integer. I don't know which integer it is. I want the solver to determine that in order to respond to one of my queries, so verification, citizens, or so on. And the way that we express the properties of the program that we care about is via assertions. Okay? So those are the 3 main concepts that we add to Racket: symbolic values, assertions, and queries. Now, I don't think I need to introduce Racket to this audience, but in the very unlikely case that you don't know what Racket is, it is a modern descendant of Lisp and Scheme. It has extremely powerful metaprogramming facilities, and Rosette uses them extensively to make all of this actually happen. And of course, Rosette also exposes them to you as the user, so you can use them as well while you're building your own DSLs on top of Rosette. Okay, so what do these constructs look like specifically? So here's the syntax of how you introduce symbolic values, how you write assertions, and how you issue the queries. I will show you through a specific example how you use these constructs to build tools in the Rosette language. All right, so here's what we're going to do. We're going to build these tools for a very simple language, which I'm going to call BV, which stands for bit vectors. In this case, we're going to focus on a tiny assembly-like language. Think of it as a core subset, the arithmetic functions that you would find in something like RISC-V. And we would like to use this language to build efficient low-level procedures. So assume that all the values in which the language are operating for now are 32-bit integers. So what this little program in the BV language is doing, it is computing the maximum of 2 32-bit integers without doing any branching. So what do we want to be able to do in this language? Well, we want to write programs, of course. We want to be able to run them. We want to be able to test them, verify them, debug them, and synthesize code as desired. So the way that we're going to do that is as follows. I will show you how to write an interpreter for the BV language. That's about 10 lines of code. And then everything else we'll get for free. And by free, I mean we'll have to write 3 or 4 lines of code. Okay? So let's see what an interpreter for the BV language looks like. Okay, so in this section of the talk, I will be showing what is happening in the DSL, or the guest language, on your left. And I'll be showing what's happening in the host language, how we're actually implementing these things on the right, in the gray area. So first, let's see how to interpret the BV language. Okay, well, the problem with the left-hand side is that it doesn't have enough parentheses, okay? So the first thing that we're going to do is we are going to parse this program into a form that is nicer. It has more parentheses. But essentially, we're going to represent a program as a list of lists. And each list represents a single instruction. The first value in an instruction is the ID of the output registers into which we're going to store the value that we compute. The second value in the list is the opcode for the instruction that we want to execute, and the remaining values are the identifiers of the input registers. So given the AST for this program, and given the sample inputs, -2, -1, here is what the interpreter is going to do. Okay, this is what the interpreter looks like, and here's how it works. So we call this helper procedure make registers, which creates enough registers, so a vector of enough registers to run this program. So this is very simple programming language. We don't have any loops. We don't have control flow. It's just straight line code. We can easily calculate how many registers we need. It's just the length of the program plus the number of inputs. And we're going to populate the first n registers with the n inputs to the program, in this case, -2, -1. The next thing that we're going to do is we're going to iterate over each statement in the program. We're going to use Racket's pattern matching to deconstruct the instruction that we're examining right now into its constituent parts. So out will be bound to a local variable called out, and that's the output register. ID, the opcode is bound to the opcode symbol, and in is bound to the list of the input register. Okay, so now that we have these, what we're going to do is we're going to eval. So we are using dynamic evaluation here. We're going to eval the opcode and bind it to a procedure op that implements this particular instruction that we're looking at right now. The second thing that we're going to do is we are going to load the values from the input registers into this local variable arguments. And the final thing that we're going to do is we're going to apply the procedure to the arguments to get an output value that we're going to store into the output register. Okay? So we're going to do that for every single instruction in our program. And we are going to return the value from the last register as the program output. So this is a very straightforward interpreter. It is very simple. Anyone can write it. A high school student, an undergrad, there is nothing special about it except that there is in the following sense. As you can see, the interpreter is using advanced programming language features. So it's using pattern matching, it's using side effects, it's using first-class procedures, high-order procedures, dynamic evaluation, and so on. All of these are things that are extremely hard to encode as SMT constraints. And this is the problem that Rosette will have, right? To take an interpreter that looks like this and to generate constraints that you can send to an SMT solver and then solve efficiently in order to verify programs in the BV language. So this is the thing that I want you to keep in mind as we go on to talk about how Rosette actually works. All right, so let's see how we would build a verifier for the BV language now that we have an interpreter. We know what the semantics of the language is. So in the guest language, in the DSL, the verification query looks as follows. It takes as input two procedures, the implementation and the specification, and it tells you if there is an input on which they disagree, and if they don't, then you know for sure that they're implementing the same function. So I'm not showing you what the specification looks like. You can assume that it is the simple implementation of the max function, which uses a branch, right? Just going to branch. All right, so here is how we are going to implement the verification for the BV language in Rosette. Essentially, we are going to use the Rosette verify query for this, and we're going to do it as follows. The first thing we'll do is we are going to use this defined symbolic construct to create two symbolic values of type 32-bit integers. So they're fresh symbolic constants. The only thing that Rosette knows about them is that they're 32-bit integers, and we're going to bind them to the variables x and y. Now, you can use symbolic values of a given type in the same way that you can use concrete values of that type. All right, so you can add them together in the case of integers. You can put them into lists. You can invoke procedures on them. All right, there's nothing special about them except for the fact that Rosette itself doesn't know their actual concrete binding. It's something that the SAT solver or the SMT solver is going to determine. All right, so now that we have these two things, we're almost done. Finally, we implement verification in BV by issuing a verify query in Rosette. So the general form of the verify query is like this. So it's verified followed by an arbitrary expressions in the Rosette/Racket language. So the meaning of this query is conceptually evaluate all paths through this expressions, whatever assertions you encounter, collect them, and then ask the solver if there is any binding from the symbolic values to concrete values such that at least one of these assertions is violated. If there is no such binding, you're done, you have verified your program, and if there is such a binding, the solver will return it, and it will represent a concrete counterexample to the correctness of your program in the BV language. So in this case, it turns out that our implementation of BV max is not correct, and the solver is going to return these two inputs. It turns out that this procedure returns an incorrect output on the input 0 minus 2, and we can convince ourselves that's indeed the case by simply rerunning the interpreter on these inputs, and it will say -1, which is definitely not right. Okay? So now, the question is, how do we fix this program? And to do that, I will show you how to debug it using Rosette and how to synthesize the fix. I will not go through the details of how that works, but I'm going to show you the code to convince you that it's as easy as doing verification. Okay, we're going to apply the same trick. We're going to implement the construct in the guest language by using the corresponding construct in the host language. All right, so here is the debug query. This is what it looks like in the guest language. It takes as input an implementation, a specification, and an input on which the two disagree. It uses Rosette to find, to issue this unsatisfiable query. And Rosette will ask the SMT solver for the core, and it will, in this case, return something like this. All right, it's going to highlight a bunch of those registers there. So we have to change at least one of those registers to make the program work on this input and hopefully on all inputs. The technical detail here is that it can be more than one core. So even if you fix it for one core, the solver may come back later with more. In this case, the example is so simple that we only have to do one iteration of this process. So here are some bad registers. How do we fix them? Well, we're going to replace them with those double question marks, and we're going to do synthesis. At the BV language, the synthesized query looks like this. We take as input implementation. In this case, the implementation contains those holes, so we generally call it a sketch. And we take the other input is the specification, and the goal is to fill in the holes, in this case by providing register expressions such that the implementation matches the specification on all possible inputs. And here is what that looks like. Here's the correct solution. This is what we should have done when we were implementing BVMax. Now, before I go on to tell you how Rosette works, the one thing that I want to emphasize here is when I'm talking about verification, synthesis, and so on in this world, the underlying assumption is that the composition of the interpreter and the program being interpreted, when you evaluate them symbolically, the evaluation terminates. What does that mean? Well, it means that every loop and recursion that you have does not depend on any symbolic values. So essentially, you can be looping, for example, over a list that's going to terminate because Rosette does not allow you to, it allows you to create symbolic lists, but not infinite ones, right? Or ones for which the maximum bound is not known. You can write a loop that loops a constant number of times, of course. That's going to terminate too. But if you write unbounded recursion, that's not going to terminate, okay? So here I'm assuming that the combination of your program in your language and your language interpreter, when you run them under the symbolic semantics, it terminates, it generates constraints, and then we can go on. Okay, so the programs are finite in this sense. Okay, so with that assumption in mind, here is what the overall workflow looks like in Rosette, kind of the cartoon picture of what happens. So we have the program, we have the implementation of your language, and we have a query. So Rosette takes this entire stack, and the virtual machine squishes it down to SMT constraints. The solver comes back with a response, and the result is lifted, again, by Rosette to something that's meaningful at the level of your programming language. So that's essentially what happens. This is the entire loop through the system. And the challenge is how to make this happen in the presence of a high level programming language constructs like the ones that we have seen in our BV interpreter? How do we actually go from something that looks like that and emit very low-level constraints? So basically logical constraints over the theories that SMT solvers, so the one that we usually use is Z3, but we support more of them. But the theories that SMT solvers can reason about efficiently. So we focus on bit vectors, integers, reals, booleans, of course, and uninterpreted functions. Okay, so how do we go from a real programming language to something this simple? I'm going to show you at a high level how Rosette works by walking you through an example. And here is the example. Suppose that we want to write a function that takes as input a list, reverses it, and filters it, keeping only the positive values. So the I/O behavior of this program, demonstrated on this input and output, would look like that. So if you give it the list 3, 1, minus 2, it should output 1 and 3. Okay, so here is a super simple implementation of this program. You can stare at it for a little while and convince yourself that it does the right thing. Here, insertion, you can think of it as adding the element to the head of the list, so cons in bracket. Now, in order for me to show you how to translate this procedure to constraints, well, we have to introduce some symbolic values and we have to issue some queries. So the query that we are going to issue here is the solve query, and the semantics is translate the program into constraints such that all of the assertions, the constraints are satisfied if all of the assertions pass. Okay, so what we're looking to do here is when somebody gives us a list of symbolic values, let's call this list V's, we would like to output an encoding of the meaning of this assertion at the end that captures the program behavior. So let's look at a very simple example. Suppose that you're given the list AB, and here I'm using colored symbols. Maybe this blue is a little bit hard to see, but A and B are blue, to denote symbolic values. So if I give this query a list of 2 symbolic values, A, B, what are the conditions under which this assertion is going to pass? What has to be true? Both of them are positive. So the translation of this program to constraints is the best translation you can come up with as a human being in your head is this one, right? A is greater than B, A is greater than 0, B is greater than 0. So let's see how you would actually go about translating this program without Rosette. So if you're doing it without Rosette, you have 2 standard options. One of them is called symbolic execution, and the other one is called bounded model checking. Symbolic execution translates programs to constraints path by path. So here's one example of how it does that for one path. We start in a state in which the list VS is bound to these symbolic values A and B, and the list PS is empty. We enter the loop, and we execute this conditional with V bound to A. So now we have 2 choices. Either A is greater than 0 or A is less than or equal to 0. We're going to explore both branches eventually, but let's explore the then branch first. So we assume that A is greater than 0, and we record this. This is called a path condition. And then we execute the then branch, and we're now in a state in which PS is bound to the list A. Okay? We go around the loop for the second time with V bound to B. And then for fun, we explore the else branch first. Okay, B is greater than or less than or equal to 0. Nothing happens. We still remain in the same state. We fold through to the loop to execute the assertion, and we see that it's false. Okay, so you can see that this faithfully encodes the meaning of this path of the program. And to obtain the semantics of the entire program, we just do this for every single path. Now, what is the obvious problem with this encoding approach? What happens to the size of the encoding? It blows up. It's exponential in program size, right? The nice property of this encoding, though, so we don't want the exponential blow up, obviously, but the nice property of this encoding that we would like to preserve is the encoding itself is given in terms of the simple primitive symbolic values that we have declared using defined symbolic. So even though our program is reasoning about lists, right? It's operating on lists, it's doing list insertion and so on. The SMT solver does not need to reason about lists, okay? It's only going to reason about integers. This is the property that we want to preserve. Okay, so let's see the alternative. The alternative is to use bounded model checking, which is going to help us avoid this exponential explosion, but it does have another problem. So let's see what it is. Bounded model checking works as follows. When we enter this loop, again in the state in which PS is bound to the empty list, we are going to execute both branches of the conditional. Okay? So we're going to execute the case in which A is greater than 0, the case in which A is less than or equal to 0, and we now have two states. The next that we're going to do is, instead of exploring the path from those two states separately, we're going to merge them into a single symbolic state and proceed from there. And this is what the merge operation looks like. It generates now a symbolic list. So PS is bound to a symbolic list. You can think of it as a term in the theory of lists at the SMT level that looks something like this. Now, the problem is, when we go around this loop for the second time, and we have to execute the then branch, we now have to encode what it means to perform list insertion. So the problem with bounded model checking is, even though it outputs this very compact encoding, is guaranteed to be polynomial in the size of your program, it is offloading a lot of reasoning down to the solver. Right? So it's now forcing the solver to reason about lists. Well, maybe lists are not so bad, but if you have any other more advanced construct in your language, it is going to leak into the constraints. Right? You're going to have to reason about it at the solver level, and we don't want to do that. So the technical problem the challenge that Rosette addresses is basically, how do you have your cake and eat it too? Okay? So the cake here is polynomial encoding, but we want it to be only in terms of these primitive symbolic values that the solvers are good at reasoning about. And the answer is to behave like model checking, to perform merging, but to perform merging differently. And here's the high-level idea. So we're going to merge values in a given state depending on their type. So if we have two values of the same primitive type, let's say two integers, flowing down from the two branches, we merge them in the same way that bounded model checking does. Okay? We just generate a term in the underlying logic. So that part is easy. It's the same as before. Now, the more interesting thing is what happens when we get two instances of a more complex type. So in the rest of this talk, you can assume that the only programmer-defined or complex type in Rosette is list. We actually support programmer-defined data types, and all of these things work for those as well. But for now, let's assume when I say complex type, I mean a list. So what happens when you get two lists of the same length? More generally, when you get two data types, two instances of a data type that have the same shape, in this case, Rosette is going to push the merge operation down. Okay? So it's going to merge A and C into a new symbolic term, and it's going to merge B and D into a new symbolic term. Okay, so this is done recursively. So if A, B, and C and D themselves are not primitive values, it will just do the right thing automatically. The reason why this helps is that the outermost list is no longer symbolic, right? It is concrete. We can operate on it using underlying racket language, right? We can do car and kudder and cons. There's no problem. It's just a racket list that contains some symbolic values. Okay, so the final tricky question is, what happens when we get two values of the same types but that have different shapes? In the case of a list, different shape means different length. Or if we have two values of two completely different types, which is definitely possible in racket, how do we merge those two things? We merge them by constructing a new kind of symbolic value. In Rosette, it's called a symbolic union. And you can think of it as a set of guarded values where, by construction, the guards are disjoint and exhaustive. Okay? Only one of them is ever true. So when the solver returns a model, one of the guards will evaluate to true, and you will know what the value of the union is concretely. All right, so let's see how this helps on our example program and in general. And the first step of the evaluation are going to be the same as in bottom model checking. All right, we execute both branches. We now have two states. So we have now two states in which PS is bound to a list of different lengths. What are we going to do? Union. We're going to generate a union, and here it is. And I am using these notations on the side to tell you what the guards are, because they're not going to fit on the slide. So you can think of them as creating let expressions as we go. All right, so the interesting thing now is when we execute the then branch on this PS value here with V bound to B, we can now execute the insertion operation concretely, right? We just push it inside of the union, and we get something that looks like this, all right? We don't have to encode the meaning of a list. We just execute it concretely on the components of the union. In the then branch, nothing happens. This remains the same. And now we come to the tricky part, and the tricky part is how to perform the merge of these two unions. The obvious thing to do, which is not the right thing to do, is essentially to take a union operation, right? Why would that be a bad thing to do if I just took the union of these two sets? It blows up. Yeah? So if you extend this reasoning, it's going to double every time, so it's going to blow up, and we didn't accomplish anything, right? So in order to prevent this blow up, when it has to merge two unions, Rosette algorithm maintains the following invariant. Every union that is ever constructed contains at most one value of any primitive symbolic type, so integer, Boolean, bit vectors, and so on, and at most one list of a given length, all right? More generally, at most one value of a given shape of a given data type. So in this case, the merged union is going to look like this. So we only have one list of length 2 that's just going to be propagated here with the guards correctly adjusted. We only have one list of length 0. It's going to be propagated here, the guards correctly adjusted. And finally, we have two lists of length 1, and we're going to merge them element-wise. We're going to end up in this state. Now, if you think about this and you extend this reasoning, what would happen if you were to analyze this query for a list of size n, you can see that the final union is going to have size n, order n. Okay? So finally, when we exit the loop, we can execute this assertion concretely. We can see that it is only true for the guard G2, so that the constraints that we end up sending to the SMT solver are these, which are exactly the ideal constraints we said we would send to the solver, and we were thinking about this manually ourselves earlier. So basically, the two things that the Rosette symbolic evaluation engine accomplishes on your behalf is combining symbolic execution and bottom model checking in such a way that it exposes as many opportunities for concrete evaluation as possible. So it's essentially a giant partial evaluator, okay, while producing this encoding that is compact, polynomial in program size. Now, polynomial doesn't mean small. So it is quite possible to write a program, to write two different programs that do the same thing, and one of them is very easy for symbolic evaluation, and the other one causes quadratic behavior. This is really difficult to debug in general, not just in Rosette, but any kind of a tool that performs symbolic evaluation. And to cope with that, in Rosette, you actually have a new thing called symbolic profiling, which is really fun to use, and it's been since implemented for other symbolic execution engines as well. But that will essentially pinpoint the causes of bottlenecks in your symbolic evaluation, and you can then fix them and make your code much, much faster. The nice thing about doing formal methods is when you're reporting these results, everything is like order of magnitude faster, which is really fun. Okay, so the last part of the talk is basically I'm going to briefly tell you about some a few applications of Rosette, and then in more detail about two recent applications, one on synthesis and one on verification. So roughly speaking, I've kind of partitioned these applications into typical PL and formal methods application in one corner, very high-level applications, so education, puzzles, games, and so on in one corner, and then low-level code, so systems, computer architecture, networks, and so on, databases in one corner. So in the programming language world, kind of the formal methods world, one of my favorite applications is using Rosette to build a verifier for domain-specific language called epics. How many of you have heard of epics? Anyone? One person. Okay. So epics is a programming language that programming languages people don't know about, but it is used to control billions of dollars of scientific equipment. So specifically, it is used to build controllers for particle accelerators, telescopes, and so on. It is also used to build a controller for a radiation therapy machine at the University of Washington. And what we did is we wrote an interpreter for epics in Rosette, lifted that interpreter to a verifier, and we found safety-critical issues in the pre-release version of this radiation therapy control software, which were, of course, fixed prior to release, and this verifier is used actively. So every time the engineers add new therapy functions, they will rerun the verifier to make sure that the code is still safe. The thing that's interesting here is that even though epics itself is not bounded, it's not Turing complete, our interpreter is not either, but the code for controlling the device is. So in this case, this form of interpretation actually does become full functional verification, which is really cool. And the engineers, when they developed this code, they actually did not do this on purpose. They wrote it in this finite way to enable testing, but it turns out that it also enables verification, which is really nice. Now, as an educator, I'm also really happy that Rosette is used heavily in education. So for example, at the University of Washington, every undergraduate, without knowing it, in the last few years, has actually run Rosette in the background. So this SQL query verification tool is used to grade SQL query rewrites, and also students run it to check whether they're rewriting correctly. This tool combines Rosette and Coq. Okay, so even if you're a Coq user in this room, and I think there are many of them, there is something for you here too. The Coq part is used for the actual verification. Rosette is used for bug finding. So if Rosette fails to find any bugs in a reasonable scope for these SQL query rewrites, Coq is then run to actually search for a proof, or to find a proof. The memory model synthesis tool is used in the architecture and systems courses to teach students about memory models. It's really fun. If you Google it, you'll find a little demo. It will allow you to interact with it online and build your own x86 memory model, which is sort of fun. This hint and feedback generation tool in that corner over there was used to generate hints and feedback for scheme programming assignments, and it was deployed in this massive introductory CS1 course at Berkeley. Okay, so that's the brief overview. Let me now tell you in details about two very different applications. So the synthesis one, as I said, super high level, and the systems one, super low level. All right, so in this particular application, what we're interested in doing is synthesizing programs that people will execute, not computers. So what are the programs that people execute? Well, whenever you have some domains that require human expertise, we can capture the expert knowledge as a set of strategies for solving problems in that domain. You can think of these strategies as rewrite rules, right? When I see something, it matches some pattern, I trigger it to produce an action. So to give you a concrete example of this, this frequently happens when you're solving logic puzzles. So something like Sudoku or the logic puzzle that I'm showing here, which is called nonograms. Has everyone seen nonograms before? Do you know what the rules of the game are? Okay, some people. So essentially it gives you this blank grid with sequences of numbers in front of each row and column. What a sequence of number means is how many contiguous blocks of filled cells are, and what is the length of each block. So all the filled blocks have to be separated by at least one empty block. When you satisfy all the constraints, you usually get a nice picture at the end. Okay? What I just described is the mechanics of this game. The game mechanics for puzzle games can always be solved by brute force search. Right? We can always do backtracking. But if you design the game that relies on backtracking, nobody would play it. Okay? People are bad SAT solvers. I mean, that's just a fact. So in order to get people to play the game and in order to generate puzzles with the right level of difficulty, what you actually need is a set of strategies that allows you to play the game as much as possible without backtracking. You can think of them as rules of deduction that are sound with respect to the game mechanics. Normally, when people design new games, they build these rules manually and they discover them through user testing. They really do this. Like they give somebody the game mechanics and say, go play the games. What are the strategies that you use to solve this particular puzzle? What we did instead, and here are some strategies for playing nonograms. So these are the documented strategies for playing this game. All right, so what we did instead is we implemented a DSL for expressing these high-level strategies, so these rewrite rules in Rosette, we gave it the tool is called nonogram synthesizer, and you give it the game mechanics. You let the SAT solver play the game, so this is how you know what the sound deductions are. And we're using these sample game states in order to extract partial specification for these rules, okay? And then the tool synthesizes an optimal set of rules, and I can tell you more in detail what all of these words mean, but essentially it's searching for strategies that are guaranteed to be sound, respect the game mechanics, and they're guaranteed to be general, okay? So they will not work on just one board state. They will work on a set of board states, on a family of board states independent of the size of the board, okay? The cool thing about this was implemented by Eric, who graduated in a few weeks, and it was able to discover strategies, a set of strategies for nonograms that outperform the documented ones. Specifically, they apply to more games, game states, and they're more general. So this games is just one application of this. We actually use the same system to synthesize rules that go into intelligent tutors that are teaching kids K-12 algebra. And for fun, we also synthesize some rules for doing proofs in propositional logic. And as experts in those domains, you would recognize some of the rules that the system comes up with. So for propositional logic, it will actually synthesize modus ponens from simpler proof rules, and for K-12 algebra, it will discover things like combining like terms, which is cool. And it will also discover strategies that are useful but that you will not have seen before because it will just find one that works. Okay, so the final application that I'm going to talk about is very, very recent. It was just accepted to SOSP 2019, and it is concerned with verifying very low-level system components. So as a brief reminder, an operating system consists of many components, and basically they cooperate in order to provide hardware services, so they mediate the interaction between the hardware and the user space, user-level applications. I don't have to tell you that bugs in the OS are really bad news, not only for the stability of your machine, but of course, they also expose you to all sorts of security risks. For this reason, there is now an entire track at SOSP called verification. Okay, so systems people are really interested in verifying these components, but each of these verification efforts takes a really long time. So right now, this is really, really hard to do. So to give you an example, so Komodo is a security monitor that was built at Microsoft Research using Daphne. There is another one called Certicos that you might have heard of that was built in Coq. So for Komodo specifically, it took 2 person-years of effort to build it. There's about 3,000 lines of assembly code, and the proof to implementation ratio is 6:1. Okay, so massive, massive effort. What we did is we built a new framework called Servo on top of Rosette that performs the same kind of verification. It's essentially proof by refinement fully automatically, so you don't need any proof annotations. And again, the implementations of security monitors specifically are all finite in the sense that I described before. So when we do verification, it really is full functional verification. So Servo takes as input a system specification. You can think of it as a functional program that describes for each system call what transition it makes on the state, okay? How it changes memory, how it changes registers, how it changes the program counter. Okay, so that is the system specification. You have some interface, you have Haskell program, Racket program, whatever you want that implements that interface, okay? Then you give us the binary that implements that interface, hopefully, right? So you will write some C code, whatever you want. You will use LLVM, GCC, generate the binary. So we support RISC-V x86 LLVMs. You can generate on you can verify at the intermediate language level as well, and this language called BPF. And then we check that every procedure or every syscall in the implementation refines the spec that you gave us. We can also check high-level properties on top of the specification, and in particular, non-interference, because there is a way to express those properties as well as first-order properties, so you don't need a richer logic than SMT. So the original verifier the first one that we built was for LLVM, and that did take, maybe a month. But each of the additional ones was very easy to implement because all the infrastructure we built for verifying LLVM code could be reused. Specifically, the memory model is the hard thing to get right when you're building these tools. But it could be reused for all these other languages. And it was done by the lead grad student in this paper, Luke Nelson, in a couple of weeks for each verifier. So let me tell you briefly about what we were able to do. We were able to fully replicate the verification effort for Certicos, as I said, the one that was done in Coq, and for Komodo, which was originally proven in Daphne. Now, what I mean by fully replicating the effort is we did the refinement proof, the binary refines the state machine specification, the system specification, which is the same as in the original systems, and we proved that the specification satisfies the non-interference properties that are important for these security monitors. The interesting part of the story here is that we actually found two issues in the Certicos system. The first one was the Certicos system didn't verify binary loading, so the proof is based on an assumption that's wrong. And the system actually does leak information because it does not satisfy that assumption. So we fixed that in our proof. And the second issue is that the specification of non-interference was too weak specifically. It didn't say anything about what a parent process can reveal to the child process. That was leaking information as well. We fixed that in our implementation as well and made sure that the proof goes through. The other thing that we did is we built a quick little verifier for this language called BPF. Does anyone know what BPF is? BPF stands for Berkeley Packet Filter. It is a language that lives inside of Linux. It allows programs from user space to download code into the kernel, and the kernel executes this. Right? There are all sorts of issues with this, and Linux has all sorts of mechanisms for defending itself against these issues, but one of the most serious classes of bugs is when Linux does just-in-time compilation of BPF programs down to the target architecture. If there are any bugs in this compiler, this is very bad news. You can actually exploit them you can make security exploits out of them. So what we actually did is we found 50 new bugs in the Linux BPF JIT compilers to x86-32 and RISC-V. All of them were acknowledged by Linux developers and fixed. And some of these fixes were done by us, so we just submitted the patches and they were accepted. And that is it. I would be happy to take any questions now.
I realized that I'm missing a mic to read questions aloud, so I'll begin by stealing yours. So thank you for the talk, and I'll begin with a question from Slido. In the BVMax example, where is my question? It's disappeared. You synthesized correct arguments for fixed operations, but could you also have synthesized other operations if the code was wrong?
Yes, yes. So I specifically made the sketch very simple in order for everything to fit in the slide. But essentially, when you are telling the synthesizer, when interacting with the synthesizer, you tell it what space of programs to explore. So I only told it to explore the space of fixes of registers, but you could have arbitrary expressions in the Rosette language, right? You could define a template to actually synthesize arbitrary expressions.
Do we have questions from the room? Over there.
Thanks for your talk. It was, I was wondering, when you were describing in the middle part of your talk how Rosette actually works, the merging operation seemed quite heavily dependent on understanding about lists that somehow sort of built into Rosette. And you said maybe you could have user-defined data types. What if I used functions? Suppose I had no lists, I just church encoded everything, right? So there's just lambdas everywhere. How does Rosette do on this merging stuff? So the shape is not now so clear.
Yeah, so in that case, it has no choice. It will just have to encode everything as unions. The same thing happens if you're using data types that are mutable and for which Rosette has to keep track of aliasing. So for example, if you're using mutable vectors, in that case, it cannot merge them. It's just not safe.
Okay, so don't use state and don't use higher order functions. Is
no,
that the sort of...
no, I mean, using functions is fine, but using procedures is fine. You can merge the procedure. You will not be able to merge procedures in the way that you merge lists. It will generate unions, but the way that people typically write programs in Rosette in Racket, this is basically not an issue. They don't use church encoding of lists. They actually just use lists.
Even I don't do that.
Another question from Slido. You mentioned you cannot recurse over a list whose tail is symbolic, basically. But what would it take to extend Rosette to support recursion in a better way? Is it possible?
I mean, basically, once you start doing that, you have no choice but to build something that looks a little bit like Daphne. So you're going to have to provide like loop invariants, recursion invariants. I want to make it clear that in Rosette, it is possible to have symbolic lists. The tail of the list is symbolic, but the maximum length of the tail is always known. So Rosette doesn't even allow you to construct programmatically a list in which the length is unknown. The length is unknown and unbounded. So you can have a list of unknown length, but the bound on the length is always known. It's always going to be known by construction, and you can recurse over that freely.
So in this help debugging process, is there any help to guarantee or to suggest that debugging is converging towards a correct program, or you can get into an endless debugging loop or iteration of debugging?
Yeah, I mean, at the end of the day, the debugging with an SMT solver is honestly pretty fragile. We include it there because it's possible, but that part is computationally intensive, even for the SMT solver. And if it looks like you're iterating too much, what you can do is just replace the entire program with a question mark, and then it will search the space of all programs of a given size, and if one exists of that size, it will find it for you.
Okay.
Thank you for a nice talk. Many SMT solvers support recursive functions and recursive data types these days. So why don't you use those features in the SMT solvers?
In my experience, they are very, very bad. Honestly, they just don't scale well enough. In all of these verification efforts, in our experience, the way to work, to use SMT solvers effectively to get them to work on real code is to stick to these very basic theories that are well understood and people, they're effective heuristics for reasoning about them. So bit vectors are really good, for example. In one of these security monitors applications, there is a loop. It has 512 iterations. We unroll it 512 times. It generates a pretty big formula, but Z3 has no problems with it.
We have time for maybe one last question from the room. Yeah.
I was curious when you said how people use Rosette. You said they write an interpreter to compile into Rosette. And then Rosette somehow mapped the SMT counterexample into the original language. Does the user need to say how to do that, or how does Rosette know how to map back into the DSL's notion of a value?
So if you want something that's very specialized to do it to your DSL and you want to have nice visualizations, you would do that. What Rosette actually gives you back is a mapping of the solver types and constructs back into the Rosette language. So if you have to do one more level of mapping, then it's easy.
Okay, thank you.
Yeah.